All right, let's just get started. As more people come in, we have a few exercises and stuff that we would be going over anyway. So welcome everyone. Hopefully the audio is working for you. I can see captions on my end, so the microphone is picking up some sound. Just as a reminder, and I realized I had to set it up yesterday, but you should be able to enable captions in Zoom today. No one requested it yesterday, but it is an option today. Before we continue, a lot of this work comes from feedback from a set of workshop surveys. So if you can, you're still able to take the pre-workshop survey. You can take that during one of the breaks or right now. And then at the end of today's class, hopefully you can take time to take the post workshop survey. All of that information really helps a lot in making sure that everything is being taught and whatever is being taught is relevant. And I need to open. All right, cool. Just as a reminder, the lesson materials you can find at ds4biomed.tech. I have it set up right now where it's just going to hover in the top right-hand corner of the screen. For the slides and papers, it's more relevant today since we will be going through one of the papers for cleaning data. You can find that at this bit.ly link. It will just open up the Google Drive folder that you can access. And then last but not least, if there are technical terms that you end up needing help with defining in the future, there is a glossary that you can open and look up definitions. Just as another reminder, if you are working on a single laptop screen, this is one way you can set everything up just so you can follow things along and not having to like click between two screens. And just as a overview of what we did yesterday and what we're going to do today. Yesterday was really just the very, very introductory. This is how you can think about setting up your data if you're coming in from spreadsheet world, and how to load that stuff into R and how to use R&R Studio to do very, very basic descriptive calculations. What we are going to talk about today is build on a lot of the stuff from yesterday's spreadsheet class. A lot of the stuff I talked about, those points about having how to set up and format your data, especially around each value should only represent one measurement or one thing. That's going to come into play a lot today. And we're going to start off with cleaning and processing data, how to think about that, how to do that, and then applying that stuff into visualization and fitting a logistic regression model and how to interpret those results. So for the first couple of minutes, and also this is some time for people to start trickling in, a recap about yesterday. So we will take a couple of minutes to work on this exercise. So open up the same ds4biomed learner project from yesterday. We're going to build off of everything that we did yesterday. You're going to load the tidyverse and read XL libraries. You're going to instead of save, I meant to type load. So you're going to load the tumor growth Excel data set using the read XL function. You're going to filter it such that it contains values from day 21, and you're going to use that set of values to calculate the average size for each value of group. And if you need some skeleton code on the right-hand side, you have some of that. So I will open up a timer on my end, and we will take a couple of minutes until 10 to the hour to work on this. And if you have any questions, just let me know, and we'll use this as a recap and as a means for people to trickle in. let me actually. There we go. For those of you on the Zoom side of things, if you want, you can type in a done or ready. If you're done with the exercise or ready to move on, you don't have to go through the exercise. Just let me know if you're ready to move on.
Hey, Dan, would you make me co-host?
Yes. All right. Okay, so let's go through this problem. I will copy the text so I have a reference for it. And we will open up our studio and so if you had set up those options from the global options that I talked about yesterday about setting up those two checkboxes and not loading things when you turn on RStudio, this is what you're presented with or something like that. The version of R might be different. But in the top right-hand corner, if you opened up the ds4biomed learner project yesterday, you would have, if you sort of hover over it, you'll see that it's pointed to my desktop and it's got the ds4biomed learner project. So I can quickly open that up on that end. And that will open up the project from that we worked on yesterday. All right, so now that we have the project opened up from yesterday, you'll notice that the file panel in the bottom right-hand corner has changed to what we, to that location. I exited it yesterday in the data folder, but we're still in this project. So I'm going to open up a new R script. I'm going to save it right away. And I'm going to call it 04 and I'll call it review. And I'll have a nice little script for review. And then here, just so I'm not jumping back and forth, I'm going to paste in the questions. And if you do Control-Shift-C, it'll take all of those lines that you have selected and comment it out. So this is code that won't actually be interpreted as code. And that's something I did yesterday, but I didn't explain. So you can also type in notes known as comments as you're working. So we did the first thing, or item number 0, which was loading up the project. The next thing here, it said load the tidyverse and read XL libraries. So we can say library tidyverse, hit Control Enter to run it, and you'll see it run or starting to execute on the bottom. And I get the little greater than symbol when it is done running and I have my R prompt back. The next part was to load up the read XL library. So the first question was to load up the medical tumor data set into a variable called tumor using the read XL function. So we're going to call it tumor. We're going to assign it some value or gets a value. The value that it gets is called read XL. And then in here, we pass in the data, medical data tumor growth.xlsx file. And again, I can specify it starting with data because of the whole working directories. This is my starting point. And so if my starting point is this ds4biomed learner folder, I can then go directly into the data folder. And I don't need series of dots, or it doesn't start with a slash or a C:// stuff like that. Next part, filtered the data such that it contains the values from day 21. So if we have tumor, we can filter data or filter the rows using the filter command such that the day is equal to 21. So before I run this, we can simply Control Enter to look at the tumor data set or click on anywhere that's not the blue arrow. And we'll see that there's a day column with a capital D. And we want to filter the rows where this day column is 21. So we can say filter where day column is equal to 21. And now you can see, you can also spot check that day has a bunch of 21s on it. The next part was to calculate the average size for each value of group. So this part of the question was a little bit ambiguous. You could have done it in any different way. Some people calculated this after the data was filtered. Some people did a new question before, just on the raw tumor data set. The main takeaway is you're then taking this data set, either the filtered one or not, because it's asking for each value of group, you know you're running a group by operation. The column that we're picking is this group column. We could have also used GRP, but group was just the one I picked. Hopefully these two end up measuring the same thing. So I'm going to say group by group, and I'm going to calculate the average size for each value. So remember from yesterday, calculating average size was using, because it's using the mean function, after a group by, we have to pass it in summarize. I can name it something, so I can call it AVG underscore size is going to be the mean of this size column. And that would be one of the ways you could have interpreted this question. The other way, sometimes people do it, is they leave out this filter. And so these two things are totally different. Not only are the results different, but the top one is only looking at the average size across each group on day 21. The bottom one is looking at the average size for each group across the entire study. Maybe that matters, maybe that doesn't. It's probably not something that's going to be useful, because if they're undergoing treatment, you expect tumor sizes to be smaller and maybe they all start at the same size. Or something like that. And so I kind of do expect a lot of these numbers maybe to show like a slight trend if there is, just because that's how averages work. But probably the values on the top, the first one where we do after filtering, is a little bit more meaningful, because we're looking at like a specific day of the study. All right, so I will copy this into the Zoom chat, just in case you need it. And we'll go on for the next topic, which is actually actually talking about processing and tidying our data. So again, just from yesterday, because someone mentioned it, all of these figures that weren't the persona figures are drawn by Alison Horst, and you can look her up and look up statistics figures or illustrations, and there's a whole repository where you can download all of them, and she has a whole bunch for a whole bunch of other statistics concepts. So feel free to use those for any type of presentation that you end up setting up. Today is the start of data wrangling, or the process of working with your data set. And pretty much the first thing you'll think about after you load up your data set is my data in a shape where I can do other things with it? The paper that we're going to cover is this tidy data paper by Hadley Wickham. It was published in 2014. Some of the definitions have evolved. I'll mention them, but for the most part, we will essentially be reading through this paper. Even if you are working with data outside of R or whatnot, I believe the first like 6 sections of this paper is like super relevant. And then the last half of the paper is actually like really examples done in an older, the precursor to tidyverse. So if anything, read like the first half of the paper, and it's a pretty good overview of what we will be covering. A lot of the data sets that we'll be presenting are literally screenshots out of this paper. So what is tidy data? What is a clean data set? In this paper, they present, here is a mock data set. Each row represents a person. We have some value for treatment A and some value for treatment B. Sometimes there are going to be missing values, et cetera, et cetera. So if I were to ask you the question, is this a clean data set? It's really ambiguous. You could say yes, you could say no. If I were to ask you, like, can you actually define a row of data? Like, what is a row in a data set? It's like super ambiguous. Or even like, what constitutes as a column? Is it just anything that I can just put in Excel? And is that enough to be considered a column or a variable in my data set? So it's a bit ambiguous, because then if I say, is this a clean data set? It's literally the same amount of information, like nothing about the contents of this table has been changed. But you can see like, hey, wait, the rows are now by treatment and the columns are by people. It's literally the transpose of the other data set I showed you. And so like, there is a difference. I mean, the definition of a row and a column is pretty ambiguous. If we go back to the last thing we did yesterday, and also like the very quick example that we review example that we just went over, looking at these two data sets, how would I go looking at these two data sets and using what I showed you between group by, selecting, and filtering? Do you have a way to say, like, I want the average treatment value across all my patients? So yes, you could do this in Excel the way you would do it. You would like make a new column in this case, and you'll say like calculate the average of all of the contents in the row, totally fine. But if you just think about the actual code you would write, there's no way you can say group by variable summarized by calculating the mean of this other variable, right? So that's, if you go back to that last group by summarization as like another way to think about how your data can be formatted, you'll notice that you can't really do it with this data set in this format. Having said that, these two forms are probably, if you were inputting data on your own, probably makes a lot of sense as you're taking or inputting data. It's just not as, it doesn't fit into that paradigm of group by and selecting and filtering, et cetera, et cetera. So in this paper, they say that, okay, if we're going to define a clean data set, this is an example of what they mean by a clean data set. First thing you'll notice, there's probably you almost would never, if you were like at least for me, if I was very quickly like doing rounds and taking notes and inputting data, I would almost never write my data this way, because it's really hard to make sure that like I got everyone's values, and the names are duplicated, et cetera, et cetera. But now we can actually go and ask the question, like, for each value of treatment, what is the average result? Or for each person or group by name, what is the average result? Or I can even say, like, just give me the average of the result column. And so we can now do those things that I showed you yesterday with this data set, and not the versions from before. And so what is actually a clean and tidy data set? Well, this is the way you want to think about your data set. And it points back to the very first thing I showed you when we were talking about just working with spreadsheets. What is a variable? So each variable is a column. Each observation is a row, and then I covered this yesterday as well, like each cell, like each value is just a single measurement. And so if we think about the data set that I just showed you, an observation is a value for a particular person and their treatment that they were on. I have variables, one for name, one for treatment, one for result, and it's not treatment A as a variable and treatment B as a variable, et cetera, et cetera. So that is the data set shape or the format that it's in when you want to start working with statistical or programming languages that work with data. And so what's sort of nice is we have a really formal definition for what makes a clean data set. The only problem is data are going to be messy in all sorts of ways, and we just need a set of basic tools to be able to handle them. And that's what this first hour is going to cover, is how do we use a set of very similar basic tools, or literally it's just 2 function calls, and we can pretty much fix a lot of data problems. Or we know it's a format of the data that's useful for one context, and then we need it to be useful for another context, and how we can switch between those two. And so the really nice thing is, once you have a tidy data set, you can then put it into a format that is either easier for a presentation or a table or a figure or something like that. And then there's like the format of the data set that is more conducive for running the analysis. So just as a main takeaway, tidy data sets all look alike, but each data set is going to be messy in each of their own ways. And if you sort of look at the words that they're saying at the bottom, we'll cover all of those problems. They're actually just talking about the problems that we're going to cover. So the first problem, really common problem that you'll see, and it's not, again, it's not necessarily a problem, but if you've never worked with data like this before, you might end up with running into roadblocks, and this is one roadblock that you might see. And this is data from the Pew Research Center, and it is for a particular religion. They gave a survey and an income bracket, and this is just a number of people who responded to this survey. And you can see this is a really space efficient data set. There's a lot of information on this one page. If I were to go and do an analysis on this, it would be harder for me to say, for each value of religion, how many people total, right? I would have to, there's no one column to take a sum of. I would have to take a sum across entire rows. And so that's another thing you want to think about when you are thinking of a clean data set, is for the most part, you want to be able to point to a column, and that column becomes the input for something else. And another thing you'll notice that these columns, like under 10K, 10 to 20K, like those are all part of a variable that is measuring income bracket. They are not separate variables on their own. And so what I like to do is, usually when I'm given a brand new data set, is I will literally take out a piece of paper. I will sketch out some of the columns from what I'm starting with, and then literally sketch out like a couple of the columns and maybe example data for where I want to be. And this would be something that I would sketch up. I would want like religion, a couple of values, income, and then frequency. So this is the data set that analytics or R or Python or data like stats programs want to use. But again, this is a not efficient format because you can see I only, given like how much space it took up on the screen, there's like very little information being presented compared to the other format. Right. So the first transformation that we're going to go through is this notion of going from wide format to long format. And if you want to look at the actual visualization, this is an animation of converting between these two figures. Don't worry about what's shown like at the top, but essentially you don't have to worry about any values being lost in this process. Just know that your data can literally be pivoted and formatted between these two things fairly easily. And that's the first thing we're going to show you. All right. So we're going to go to our studio. We are going to open up a new script, and I am going to save this as 05 tidy because that is the next thing that I worked on. All right, so like I mentioned yesterday, if you are working on a new script, it's a pretty good habit to essentially go to session and restart R. You'll notice I had that tumor data set loaded up before, but I want it out of here because this way I'm only focusing on the stuff in this particular script and things aren't like being carried over. Because this is a brand new R session, we do have to reload everything again. So I'm going to say library tidyverse, and it will open up tidyverse and reload the library. So we're going to look at another data set. It's another format of the tumor data set. So I'm going to say tumor is going to get read underscore CSV. And we are going to look at the data folder. And if we look at tumor growth, there's actually one called long, and this is the long example. It's not in long format yet, but it's the example that we're going to be in. So we're going to load up another format of the tumor data set that we've been seeing. And if we open this, this is very similar to the data set that we were. You'll notice that the days are now in separate columns. And again, this is a really space efficient view of the data. I very quickly know that I essentially have 37 people because there's 37 rows, and I didn't have a separate value for each day, right? So if you are putting together data and you have multiple people, and you know there's other research projects going on, this is a really good way to make sure that like, hey, like maybe I need to call someone to come in, or maybe they were scheduled for something, and you'll see not every single person has a value in this data set. And that's something a little bit easier to catch when your data is formatted this way. But one of those hints, like I essentially call them like data smells, is one, it's not the fact that it has a lot of columns. It's the fact that if you look at the columns, a bunch of them seem to be all related to the same variable. And that's the thing you want to keep in mind when the first thing you're given a data set is, okay, at least at least you're given a data set that's sort of in like this nice rectangular tabular format. And then the next thing I usually notice is looking at the columns and saying like, oh, what is 0? That's a little weird. And then 1, 2, 3, 4, 5, and then it goes up to 28. So this is probably days or some kind of count. And then this is some kind of value in there. And then the 0 to 28 are all part of a single variable. And so that's how you know that if you want to do the analysis of this, like I showed at the end of the day yesterday, where I can say group by group and calculate the average value, etc. It's much easier to do that. Likewise, there's nothing wrong with this format of data set. If you had your data in this format already, this sort of does save you the step that we did where it was like filter on day equals 21 or day equals 13, because now you can say group by group and then calculate the average or the mean on the column called 21, right? So there are use cases for different formats of the data. But just so you know, there is a more preferred format of a data set. And again, you can see in this format, yes, this study only lasted up to 28 days, but then you have to think about, like, are you just going to keep appending columns to this if the study goes on indefinitely? And then, like I said, a lot of programs literally will have like limits on the number of columns that you can have in a data set. So these are things that you want to keep in mind. So this is our tumor data set. And again, I can also type in tumor and then running Control Enter, just look at the tumor on the bottom left-hand corner, and it will print out on the console. All right, so how do we go and fix this problem? The way we fix this problem is we take our tumor data set, we pipe it into a function. And this transformation is essentially, if we were to sketch out the problem, has a lot of columns, and then we want fewer columns, but more rows. So it's literally pivot underscore longer because we're making the data set longer versus wider. So the function we use is pivot underscore longer. It's a function within the tidyverse, and it does this exact operation. You pick a whole bunch of columns and it will pivot them into a longer format. The way we do this, so pivot longer, the first input is going to be a data set that we want to pivot. So that's why it's in this notation. The next part of the syntax is you want to select all of the columns that you want to pivot into longer format. So yeah, we could say 0, 1, 2, 3, all the way to 28. That's a lot of typing. That's also, you might end up with a lot more problems than just typing. You might have typos, et cetera, et cetera. So R and Tidyverse has a lot of other tools to help you select a bunch of columns. Like yesterday, we manually typed out a couple of columns that we wanted to keep, but what if we're running a GWAS study and we wanted like this, all of the SNPs in this one chromosome, and we just want this entire range? It doesn't make any sense to like literally start typing that out. So if we know the starting point of a column and we assume that the data set's not going to get shuffled, and the ending point, we can specify the first column, so 0. Other things about column names in a lot of variable names and column names and stuff, they do not like starting with numbers. So if you can, instead of just a 0, maybe put a D0 or day 0 or day underscore 0, etc. So that's why I have to use these backticks to refer to the 0, because I'm saying like, I mean 0 like the actual character 0, not like 0 the number. In R, if we want to select from one point to the other, we can use a colon, and it says start from 0, and then we can say end at 28. And that will select all from 0 to 28. And if I run this, if I spelled it correctly, if I run this, we essentially get the data set that we have been working with yesterday. It took all of that stuff and pivoted longer. It gave us 2 default values called name and value. We can fix that in a little bit, but this now is that data set, and we can ask the question, for each group, give me the average value, or for each group and in this case name, give me the average value, which is a tumor size. And that's all done by this one little function call. So let's clean this up a little bit. Let's say your data set is it's still in progress, right? So we don't want to end up saying just hard coding the 28. right? Because we're going to hit a point where something happens, someone tells us to rerun the analysis, we just rerun and it's like, here are the tumor sizes, or here's the averages. And we forget that it's going to the 28, even though the study is continuing. So there's a lot of other helpful selectors that tidyverse gives us. One of them is also last underscore col with round brackets. And this will find the last column of your data set. So now if you're adding more data, it doesn't matter. You can just rerun this script and it's always going to be up to date. So if you go to day 28, 29, 30, et cetera, your analysis will keep up with that changing set of data. So if I run this, you'll notice that you literally get the same set of results because 28 is also the last column in our data set. So the next thing, since we're in the process of cleaning our data, let's make our columns a little bit more useful. And so how do we change these columns? So if you ever forget, again, you can put your cursor between right before the opening bracket, hit F1, and it will open up the little help panel in the right-hand corner. And so if we look at pivot longer, there's a whole bunch of stuff in here, but if we scroll down, you see the option for names too. So it says a string, which is single or double quote, like name of the column you want to create. So essentially it's saying, how do we rename this name column? And if we scroll down a little bit, there's other stuff, but the other one that we are going to be interested in right now is one called values to, which is another string specifying the name that defines this. So if you want to read more about what you can do with pivot longer, or if you forget like, hey, how do I just rename those columns? That is how you can slowly work on reading the little help documentation for it. So we're going to say in this pivot longer, we're going to pass in a few more parameters in here. So it's separated by a comma. And the first thing is going to be names underscore to. And you'll notice that RStudio does try to be helpful where if you are within the set of round brackets, and if you sort of start typing and wait a little bit, or if you hit the tab key, it'll notice that like, okay, I know all of the inputs for this function. Let me help you figure it out. So if you know it's like names, something, hopefully this will jog a memory into what parameter you need. So names to, we're going to call this name column. What are we going to call it? We'll call it day with a capital D. And then the other one is values to. So you'll notice that like I typed in VA, hit tab, and it automatically popped up like, hey, these are the other inputs that begin with VA. So values to. And then in single or double quotes, it doesn't matter. I'm going to call it size. And now if I run this, I have a pivoted data set with day and size as inputs. And so if this looks good, I can then say tumor underscore tidy, save that to a value. And now I can do that, essentially that problem that we worked on this morning and yesterday, where I can say group by group. And then let's also do it by day. And then I can summarize average size is equal to the mean of size. Sorry, it's lowercase d because I renamed it that. So you'll notice here, because my data set, remember in the untidy format, there was a whole bunch of missing values. So like, let's say right here, there's a whole bunch of missing values. So the way the mean function works, if I sort of play around down here, 1, 3, and 5, what is the average of 1, 3, and 5? It is not 1. That is weird. What is going on? Oh, I know what's going on. Oops. Okay, so mean, I needed to put in 1, 3, 5 as in one group, not as separate things. So in R, if you want to pass in, remember yesterday when we used the poll function and got like the sequence of values, we can use, if we want to manually create the sequence of values, there's a function called C, it stands for concatenate. and we can concatenate values, so 1, 3, and 5. So the mean of that sequence, so 1, 3, and 5. So this looks like the output from poll from yesterday. The mean of that sequence is 3. But if I put in capital NA, so this is R's way of saying missing. Every programming language has a different way to say missing. If we put in what is the mean of 1, 3, 5 and missing, the mean function doesn't know how to calculate that, right? Because you literally have a missing value in there. It's just, I don't know what you want to do with this, because if I give you 1, 3, and 5, you're dropping a value, and you should be more explicit about that. Or if I do 1, 3, 5 and missing, and I use 4 as the denominator, that's also something you need to be aware of, because essentially it's treating it as a 0. So what do you do with this? For most cases in the mean function, if you hit the little tab key, there is a little parameter called na.rm. And this says, so na is missing, rm is the computer way of saying remove. So here is the mean function can automatically drop missing values. So if we say na.rm equals true in all caps, so that's how in R you say yes or true. Different languages have different ways of saying true and false. R is all caps. Now if we run this, it will drop the missing value in that sequence. And so how does this tie back to what we worked on? Well, if we run this calculation again, it's not just for group 1, day 1, not everyone has a missing value. It's because someone in there has a missing value. So in our mean function, we have to say na.rm equals true, and then it will drop those values. And now we have, for every group and every day, we have an average size. And so this is another way, export this out to Excel or filter by group and export those separately. And then you can compare or draw line graphs, or I'll show you how you can draw line graphs. But that's how you can slowly start the process of using all of these skills and start stitching it all together. And that's all because we were able to pivot into a longer data set and then still build on the stuff we covered yesterday. So again, this pivoting step between wide and long is like one of the most important things you can know about when processing data, because like yesterday, one of the questions was like, what if you had like heart rate in separate columns? Like, that's totally fine. You now know you can use this pivot longer function to make it so you can have a data set that is more conducive for some other analysis later on. All right, next common data problem that you will have or run into is this notion of multiple variables stored in one column. And if you've ever downloaded data from the CDC website, I usually equate this. I see this a lot in health data sets. And it's part of it is also because, again, it's very space efficient. And so this is data from the WHO. It is for every country year, it is a count of tuberculosis cases. And so the problem, if we look at these columns, what do these columns mean? So let's say I'm looking at this 228 here. That 228, if I look at the column, says M1524. So that column stands for that M stands for male or female. So if you look here, there's an F. 1524 is an age group. So that 228 stands for, and I don't know the country code for AF. So in the country AF in the year 2000, there are 228 cases, male cases between the ages of 15 to 24. So that's how this data set is set up. It's a little bit truncated. So we have males 0 to 14, all the way to males unknown, and then female 0 to 14. And then this data set has all the way up to female unknown. So this 228 has this problem that's like literally bolded at the top. There's multiple variables associated with that number. So what is that 228? It stands for two things. It's not just one thing. It is a gender value and also an age group value. So that's a problem. That's another problem you'll have. Hopefully you don't end up putting together your data set like this, but this is definitely the format of data you'll get in a lot of like public health data sets. They just give it to you like this because it fits very nicely in PDF reports. So how do we fix this? Well, part of the problem is the same problem from before. If we just look at the column names, this M014 all the way to female unknown, like that entire thing, they're actually just measuring the same variable. It just so happens that that variable is two variables all in one, but it's the same thing. So the way we fix that is literally the same thing that we did before, which was that pivot longer step, right? So if we do that, we get the data set on the left. And so that's part of the way there, right? Because at the end of the day, I would like a separate column for male, a separate column for gender, and a separate column for age group. And then I can ask the question for each year, what are the case counts? And I'll get yearly case counts across the entire world, right? That's something I couldn't do before. And so if I look at the data set on the left, I am almost there. And if I were to ask you, forget everything about programming, like how to program the problem. And if I were to be like, okay, I have this column, it looks like this. If you could just will this into existence, how would you go about making the data set where the sex or gender column is separated from the age group column? So there's a few ways you might think about how to do this. One way would be like, well, it seems like the first letter of that column represents the sex, and then everything else represents the age group. So if I could just pop off the first or chop off that first letter and make that the sex column, and then the rest is the other column, then problem solved, right? Another way you might think about this is, well, it looks like the age group is only numbers. So if I can just separate things that are letters and things that are numbers, that's another way you can do a separation, right? So there's multiple ways of doing the same problem. And you can all do that in R. And so that's why a lot of times people talk about like data science being an art, because it's literally just like which one of those methods is easier to you or easier to other people or easier to calculate or less prone to like another human typing in results, et cetera, right? So you might end up in a case where like, instead of just using M014, somewhere down the line when someone's inputting data, they type in MALE014. And then your whole workflow of like using the first letter no longer works, right? And then you go into the, okay, now I have to search for numbers and instead of letters, et cetera, et cetera. So there's different ways you can deal with that. All right, so let's load up that data set and see how we can go through that problem. All right, so we're literally going to go and load up that same tuberculosis data set. So we're going to say TB gets read_CSV. And we're going to go into our data folder, and there's literally a TB_long data set. I can click on the TB thing on the right hand here, and you'll see that this is literally the data set presented in this paper. So this is the tuberculosis data for each country, year, gender, and age group. All right, so first problem, we need to go and if I look at this data set, remember the order of the problems that we're trying to fix. The first thing we want to do is take those columns, pivot it down just like the previous example. So let's go and do that. We can say TB goes into pivot_longer. We want to select everything from this M014 all the way to the end, right? So it could be M014 : last call. That's one way you could have done it. That's totally fine. I talked about there being multiple ways to help you select things in R. So instead of just showing you the same exact process from before, I'll show you a different one. There is another way you can select columns using something called, using a special type of selector called starts with. So I want to select all of the columns that starts with, I have to put in multiple things. So it's not just like, if I look at these columns, what are the columns I want to select? It looks like if it either starts with an M or an F, I want to pivot, I want to select those columns, right? So I want to specify two things, just like how in mean, if I wanted to specify multiple things using the C function, if I want to specify two things in this case, I have to use the C function again. And if it begins with an M or if it begins with an F, those are the columns I want to select. And this type of selection is a little bit more complex from what I showed you, where it's like colon last call or colon female unknown, et cetera, But this format is really useful if you end up with survey data, because you can then say, I want to select columns that are like Q4.2 or the Q4 questions in this survey, and then get you all of the survey questions from there. All right, so we can run this and we get that same problem as before. It got pivoted down and it's the left-hand side of the data set from the presentation. So we can choose to save this now. So let's call this TB long, just so it's something that we don't have to rerun that block of code again. And then the next step, remember, was given this data set, I just want to separate off of the first column. You could have done it in other ways, but let's just use the first column example. So given this data set, TB_long, there is literally a function called separate. Separate takes in a data set, and then you give it the column you want to do this splitting, like pattern splitting thing that you're going to define. So in our case, we're going to work on that name column. When we do the separation, how many columns are going to be created? So when we split up this name column, it's going to create two new columns. In our case, two new columns, one for sex, one for age group. So there's a parameter called into. So we're going to separate the name column into two columns using C, one for sex, one for age_group. And then there's a parameter called sep, where we tell it, how do you want to do this separation? So we can either provide it a pattern. We're not going to go through like regular expression patterns, but you can say like characters and numbers are going to be the dividing line. You can do that. But in this case, you can also give it a number, like split on the first character. And then what it will do is it will do what you said, split on the first character. And then when it does that split, create those two columns that you provided, sex and age group. And then that's it. So now you've just processed that column. Sometimes in data sets, you might have to do that multiple times. So you might have to do this, clean it, and then do another pivot, clean that. So depending on how your data set is formatted, you might end up doing this once, doing it multiple times, et cetera, maybe doing it once this way and then exporting it out, except whatever you need. And so now we can save this as TB_tidy. And now we have our TB tidy data set. And if we want, we can go through the example like, now you can say like across all of the countries in the world for all time, like what is the number of tuberculosis cases? And you can take a sum of the count column. Or you can group by the year and age group and then get a sum instead of a mean of the count column. All right. So the last really common data problem that you'll end up with is this problem where variables are stored in both rows and columns. This is a situation where you don't really know it exists, but you sort of like see data and you recognize like, what is the first problem that you see here? Well, it looks like D1 to D whatever looks like it's measuring the same thing. So it's literally the same thing we've been talking about. So this is data from, I think, I'm getting my data sets confused. I forgot where, but for a given location, year, month, and day, there is a specific temperature reading. That reading is either a max reading for the day or a minimum reading for the day. So the first thing in this data set is, if you look at the columns, D1 to whatever seems like it's measuring, again, the same variable. So we know how to deal with that problem right now. There's going to be a pivot longer step involved. So when you're processing your data, just work on things one at a time, and then you'll maybe notice an additional problem later on. So if we do that, we get the data set on the left, which is after pivoting longer. And then maybe this is all you need, because this is useful because you can say for each date, and then group by date and group by element, calculate average value. That's really useful because then you can get temperature min and max all in one calculation. But if you ever end up in a situation where like a bunch of values in the row is duplicated, like the things that define the observation are duplicated, like age and date, that is defining the temperature value, and then the only thing changing is like one or two other things. That is one of those like data smells that like you have data stored in like two axes. And so what might be useful, or another way you can say to yourself, what is your unit of measure? I'm trying to measure temperature for a given day. So each row should be like one date for a given location or an ID. And then I get temperature min and max. And so as far as tidy data sets go, you might have the data set on the right. And so the opposite of pivot longer is pivot wider. And so in order to get the data set on the right, we pivot the one on the left wider, and that's the other or the opposite transformation. And so we can also do that in R, and I've been saying it, it's literally called pivot wider. So let's look at this other data set for CMS utilization. So in the United States, this is Medicaid. Medicare data, sorry, Medicare data. So this is, I got from like the CMS website, and the actual data set doesn't come in this format. I had to like make it a teachable format, but we can read in this data set. It's under data, and it's called CMS utilization.csv. We can look at this data set either by just running CMS or clicking CMS here. And you can see here, for a given state, a state has a FIPS code. There is a particular variable like per capita spending annual, gender for age 65. So this is CMS utilization by state demographics, year, and some kind of measurement like per capita spending or whatever. And then here, number of chronic illnesses, and then this is the spending value across all of these years, right? So the first thing I'll notice is like, okay, these are the years, probably a column if I want to do like other types of analysis, that is going to be a pivot longer step. It's just something to keep in mind. If I scroll down a little bit more, you'll see that like the measurement is also like not just per capita spending, but there's also hospital readmissions percentages, et cetera, et cetera. And so that's what's in this data set. So I noticed that the years have they're in column. So the first thing that I would want to do is turn it into rows. Again, there's nothing wrong with this format of the data set. One thing that could be really useful is, let's say you're trying to find the observations where per capita spending was under 2,000 in the year 2007, but more than 5,000 in the year 2010, right? You need the data in this format to do that type of filtering. And so knowing how to go back and forth between the two also helps you filter your own data set. So even if I gave you this in tidy format where year is in its own separate thing, there's no way for like to filter a row based off of, in itself, essentially. So you need it in this format to be like, I need like Alabama values under 2000 for 2007 and over 5,000 for 2010. Like you have to have your data in this format. So the first step is, again, pivot longer. So we have CMS is going to go into a function called pivot_longer. And again, I've talked about a bunch of ways that we can do this. So I'm going to go back to the first way, which was 2007 : last _call. So we're going to select all of the columns from 2007 to the end. Another way you could have done it is like, if the column is a number, like starts with a number, you could have done that as well. I'm just trying to avoid like specifying patterns, but that's something you can do as well. And then I can say names _2 is going to be called year. So when I run it, I get year and value. I'm leaving value because that's the default name, so I don't have to re-specify it. You can also call it cost if you want to put in the values to parameter. And so that's CMS. That's this long form of this data. So now if I look at CMS long, I can save this because this looks like something that's worth saving. If I look at this, you'll notice that other than year and value, if I look at a particular row, a bunch of things are getting duplicated. And it's getting duplicated primarily because of this one variable column, right? So it would be really nice if I just got, for a given row and year, like all of the types of spending that's going on instead of spending being individual values. Or you can leave it this way, and then you can just use this variable column as a group by variable and say like for every given state, group by state and value, give me the average cost, right? So you can do that as well. But in terms of like storing data or just going through the exercises of pivoting data in both directions, we now have this other problem where we have this variable column needs to go the other way. So we can take this long data set, CMS long, we can then pipe this into a function called pivot_wider instead of longer. And the way pivot wider works, so if you think of pivot tables in Excel, you select the column you want to pivot out. So in our case, it's going to be called variable. And then for each unique value in that column, it's going to create a new column for it. So pivoting out that way. When it does that, you need to select another column, and that column defines the values it's going to use to like fill in the new parts of the table. So those are the two things you need to specify. So the way we do that is there's a parameter in here called names_from. And we're going to say like for every unique value in this variable column, so we're going to say variable. When it does that pivot, we're going to pick the values from this column called value. And so now if we run this, I'm going to call this CMS tidy and save it so I can also show it to you in a bigger screen. Now I have a data set for a given state, FIPS code, demographic information year. I have per capita spending, standardized, ED visits per 1,000 beneficiaries, hospital readmissions rates. That is all in one row of data. So this format is useful because if we were to be fitting models, we can literally point to that column, the hospital readmissions column, right? We can now point to columns. So even though in the previous format, if we wanted to do something like quick averages, we don't have to type all of these 4 columns. We can make it longer, use that as a grouping variable to do that, totally fine. But if you're thinking about creating visualizations, or if you're thinking about fitting models, you have to point to a single column. And this is what allows you to do that. Right. So this pivoting, the CMS code here, just so if I want to, if I were to be doing this for real, I would end up writing this like this. So it's literally the same block of code, except I'm taking the original CMS data, pivoting longer, realizing there was another problem, piping that into pivoting wider, and then saving it that way. So you don't have to save each intermediate. You can if you want. There's nothing wrong with that. If you're starting off and you're learning for the first time and you're kind of don't know what's going on with this piping, it's totally fine to create multiple variables. Just so you know, you can also do this in this one kind of piped code format. All right, so that's one of the core principles when you are working and processing and tidying data. It's probably the first thing that you're going to identify and end up doing before you do anything else, because a lot of plotting libraries and model fitting libraries and any form of statistics requires you to point to a column. So again, think about the group by summary, like if that's a mnemonic to help you remember like how you need to format your data set, like can you group by this and calculate something off of that? If you can't, it's probably one of these data pivoting steps. So make friends with tidy data. It will essentially make your life easier, make storing data easier. Your statistician friends will all thank you for doing for making your data set like useful. And also the other thing you'll notice is in the process of cleaning your data set, you fix a whole bunch of other problems, right? So now like before when like, for example, gender and age group was all mashed together, they're totally separate now, right? So those are part of the data cleaning processes, and everything else essentially stems from that core principle. Usually I have like an exercise to work on, but I can't find it. So we'll just take like a quick 5-minute break right now. So come back at, according to me, 15 past the hour. And if you have any questions or whatever, just let me know. All right, so the next thing we're going to talk about is an introduction to visualization, specifically how ggplot2 works in R. So this is going to sound super basic in the beginning, but whenever you have a column of your data set, there's two things that ends up happening. One, everything in that column is going to be the same data type. So if you have mixed data types in your column, probably something not specified correctly. For example, M0 to 14 was sort of like this weird mixed type kind of ordeal. But when I say type, I also mean how does the computer represent that thing? So it's either a bunch of letters and numbers and categories, so known as a string or a category, or if it's a number, then it's either a continuous number or other types of categories in your data. So you have things like nominal data, which is just discrete categories, like gender would be one of them. I would almost say things like treatment group is going to be another one of them, because there isn't typically an order to the treatment groups. Usually the control is just a reference. It doesn't mean it's better or worse. You have ordinal data. So these are things that are categories, but actually do have an order. So like, how happy are you right now? Or Likert or Likert scales, those are ordinal data. And then another type of variable that you will probably encounter is a subset of ordinal data, or really a subset of nominal data, which is a binary variable. In a lot of health contexts, a lot of the analysis is done around binary data. So it's either counting two groups of something. So if you've heard of 2x2 tables, those are literally two binary variables that you're counting. If your question can be asked in a yes or no question. So like, did this person respond to treatment, yes or no? And then you define treatment elsewhere, or did this person survive, yes or no? Or was the whatever treatment effective, yes or no? So if you can ask your question in that way, then it's a binary variable. And why does that come into play? Because depending on the type of variable that you are working with, that heavily dictates the type of visualization that you will need to make. Where is my mouse? There we go. All right. So how does ggplot work? So this comes from Thomas Lynn Peterson's ggplot2 workshop on YouTube that he gave a year ago or something. So Thomas Lynn Peterson is the current maintainer of the ggplot2 library in R. And so from this slide, he tries to break down all of the components that make a ggplot2 figure. And the GG part of ggplot stands for grammar of graphics. So there is a grammar or ordering or layering of different elements of a figure. And so if we start from the bottom, working our way on top, the core component of a figure in ggplot is going to be put into the data layer. And just having a data set is not useful in the sense that like, here's some data, like you haven't told it what to plot. So in the mapping layer on top, that's where this is also where all of that tidy data stuff comes in handy, because this is where you literally start pointing to columns and saying, I want this to be the x-axis. I want you to count this column, or I want, a whole bunch of points, but I want each point colored differently based off of that column. So the mapping layer is how you specify your columns. And if your data set isn't tidy, you aren't able to point to a column. And so that's how all of this is slowly starting to get related and put together. Next, the next couple of layers, the statistics and scales layer, typically you don't have to specify unless you are, when you go and try to make the figure, usually the statistics and scales layer is like calculated for you automatically, but it does give you the option of manually tweaking it. For example, if I had if I had raw data sets of, that tuberculosis count data, so instead of age group, I just had individual people and whatnot, I could say, give me a bar plot. A bar plot is usually counting something, counting a categorical. So I can either, the bar plot itself will just, I can just give it like, count all the unique values in this column and it will give me a bar plot count. Or I can do the group by aggregate sum in advance, and then here are the actual data like already pre-calculated. You don't need to do anything. So that is like one example of like, do you want the plotting library to do the counting for you, or have you already counted everything? You just want the plotting library to just put the number. So that's what's in the statistics layer. The scales layer is stuff like, do you want to log transform something because it's exponential growth, et cetera, et cetera. So we haven't actually talked about the actual plot yet, like a bar plot, scatter plot, violin plots, box plots, et cetera, and that's done at the geometry layer. So the wording for geometries is sort of important because it plays into the role of how you can pick a figure, but the geometries layer is how you say, like, I want the scatter plot, which is in ggplot language is called a point plot. On top of that, and this is a little bit easier to show you in actual examples. So there are facets and coordinates and like color themes. So facets, I will show you later on. It's just easier to show than to explain it without showing it to you. Coordinates, these are things where like, do you want to change it from regular Euclidean points to polar points? So you can make like these circular plots. Coordinates also play a role with plotting maps, because you're now on a different plotting axes system, and map projections all play a role into that. And then themes are literally just like the fonts and colors and stuff like that on your plot. So all of that will create a figure that you will hopefully be happy with. So we're going to open up R. I am going to create a new script because we are up to the next part of our lesson. I'm going to call this 06, and I'll call this ggplot. And I'm going to hit reset session and then restart R, just so we are starting off of a clean slate. And I am going to load up a couple of data sets, couple of libraries. One of those libraries is going to be a data set. So we're going to load up tidyverse, although I don't, yes, we'll still use tidyverse. We're then going to load up ggplot2, which is our plotting library. I believe tidyverse technically loads it up for you already, so you don't have to worry too much about it, but it's kind of better to be explicit. And then one of the setup steps was to go and download this library called medical data. This is a package created by Peter Higgins, who is a physician in the University of Michigan, and he has curated a whole bunch of medical data sets. They're real medical data sets. They've all been anonymized and de-identified, and he has created a package in R that we can load up, and it's all just data sets that we can work with. So the data set from medical data that we are going to work with is the blood storage data set. And I am just going to sort of just read the description. So this is a retrospective cohort study of 316 men who have undergone a prostatectomy and received a transfusion within 30 days of the surgical procedure, and has some available PSA follow-up data. And then the outcome of interest is whether or not there was a chemical, biochemical marker for cancer reoccurrence. And so there's going to be a couple of variables in here. When you are given a data set, the first thing you want to be able to identify is like, what is the variable of interest? Our variable of interest in this case is going to be whether or not there was a marker for cancer reoccurrence. So how do we look up this data set? And I probably should have done this before I read the example, but after you run library medical data, there should be a variable automatically created for you called blood storage. One thing you will notice is that the printout for blood storage is a little bit different from all of the data frame stuff that we've been working with. So if you remember, there's this function called class, and if we give it that, it is a regular pure data frame object versus everything from up until now. It was like a tibble.df data frame. So this is the plain R data frame object, not the data frame object coming out of tidyverse. There aren't any differences that will affect your analysis really. One of the things that really points out immediately is like the printout it's not as pretty of a printout. Like it's giving you all of the rows and not all of the rows, but many more rows and many more columns, and it's just wrapping around. And if you look at underneath the column, it doesn't tell you like what type of data is being stored. Like it used to say like, hey, this is a character, but so that's really the only, I guess, a practical difference between all of them. Also in this data set, I mentioned this yesterday, there is a function called names. And if you are trying to get all of the column names in your data set, you can run names of this column of your data set, and it'll give you just the column names. And so if you know your data set, like what is the actual variable of interest, I am probably going to say it's probably this column called recurrence. So that is probably the variable we want to use. We want to explore this variable, see what the interactions or other correlations with this variable are. When we go and fit our model, this is the variable that we are going to be interested in. And then there's other demographic stuff that we can slowly start to explore. So given a data set, and as we start going into visualization, because eventually we are going to fit some kind of statistical model off of, few things you want to be able to identify. First, what is the variable? Again, what is the column of interest? Depending on what field you're coming from, this is either called the response variable, it is either called the dependent variable, it is also called the Y variable, or it's called the outcome variable. Those are all synonyms for the same exact thing. So you want to be able to define your Y or your outcome. And then given your data set, you want to be able to figure out what your predictor variables are. Sometimes they're also called the independent variables. Sometimes they're literally just called variable, or what are your X's? So you'll hear people say like, what are your X's and what's your Y? So the Y is going to be the variable of interest, and then the X's are like all of the inputs. All right, so let's do a bit of data exploration on our current project, on our current data set. So let's say we have our blood storage. Our variable interest is this recurrence variable. So let us group by this recurrence variable. And then I want to summarize and then just get the count. I want to see like, this is the variable of interest. It is binary, like whether or not you had cancer recurrence, yes or no. So I just want to get a count of what's in here. So I can say CT is N, the function. So that literally just counts how many rows of data you have in this data set. And so here, recurrence has two distinct values. So it's either 0 or 1, and you will go and look at the code book and say like 0 stands for no recurrence, 1 stands for yes, there is a recurrence. And then the count is 262 no's and then 54 yeses. So this, at least from this data set, it seems like the recurrence is like relatively small, or it's not like totally rare, but it's infrequent. So when you are doing the analysis of your data set and you're going to go and fit a model, knowing your response variable is really important. And if it is a categorical variable or if it is a binary variable, you definitely want to be able to get a frequency count on them. Because if you were to go fit a variable, and let's say like we make this even more extreme, let's say I have 100 responses, 99 of them do not have a cancer reoccurrence, but one of them does. If whatever model I go fit, it's probably just going to say no for everyone. It doesn't matter what inputs I give it. It's just going to say no. And if you just look at the model from that perspective, it is correct 99% of the time, right? So it's really not accounting for like the thing that you actually care about is like, no, we really want to actually identify whether or not someone's going to have cancer or not, right? So this is a problem in data science or statistics or machine learning. It is a problem called class imbalance, where there is a class, recurrence is a variable. Each one of those categories is considered in jargon form, they call it a class, and there's an imbalance between the classes, right? And so how do you deal with this? You either use all of the people from one and then literally randomly sample the same number of people that have the value of 0. That is one way you can deal with this in a machine learning context. And there's other techniques and other ways that you can work around class imbalance, but that is the first thing you want to be able to identify is if I just go and fit this model, is that model coming out going to actually be something useful? Because if it just 99% of the time says one thing because my input data is imbalanced, it's not really going to be a useful data set, right? And this also plays into the world of ethics where like, you read stories about they started creating models whether or not to give people parole out of jail. And then you just find out that like no one gets parole out of jail, but it just so happens that like 99.9% of the population is Black. And then so it's also because your input data is all like that. So class imbalance is something you definitely want to keep track of. And you can identify that with frequency counts. So descriptive statistics. But now let's go and actually plot a figure. Let's make this an actual figure. So I talked about ggplot and all of its layers. So we have this function called ggplot, and that's we're going to put in the data layer. So data equals blood storage, right? So remember the different layers that we put everything in. So the first layer we're going to input is this data layer. Cool. You'll notice that the plots panel on the right-hand side probably opened up, and here's your plot. It is literally a gray square or a white square, depending on the contrast of the screen. And this makes sense because, again, we didn't tell it to do anything. We just said like, hey, here's some data, right? So if we go back to our figure, what's the next thing that we want to specify? We want to specify this mapping layer, which tells us which columns we want to use. So we will do that. We're going to say comma, we're going to say mapping is equal to what are the variables that we are going to map. This is more of an analogy, but similar to how we use C to specify multiple things. In ggplot, there is a function called aesthetics, AES. That is how in the aesthetics function is how we specify the variables of interest that we are trying to plot. So, all right, so what is the variable we're trying to plot? Well, we're trying to plot the recurrence variable. So we're gonna try to make a bar plot because we're just trying to count the number of observations. So we're going to say X is going to be recurrence. And if I run this, the plot sort of changed, but we didn't really get a plot yet, right? And if you go back to our ggplot layer, okay, and it's because we haven't specified the geometry layer yet. All we said was, here's some data. I want you to plot something on the x-axis. I haven't told you what exactly to plot yet. So how do we add on the geometry layer? We literally put a plus, and then we can add on the next layer of information. how do we find out our plotting layers? So if we say geom underscore and let R and RStudio do the auto completing, anything that begins with geom underscore is the object that you can plot, right? So you can create area plots, bar plots. That's the one we're going to pick. You can create bin plots, box plots, density plots, et cetera, et cetera. You can add error bars to things. You can create histograms. I can just keep going. Point plot is ggplot's term for scatter plot. So I'll show you that in a little bit as well. But geom underscore is how you can find all of the different types of plots. The plot that we are trying to do is geom underscore bar. Oops. And if we run that, we get our figure from ggplot. So on the x-axis, we told it to plot the recurrence. And because it's geom underscore bar, bar plots understand to do counts. And so because our recurrence value only has values of 0 and 1, it is counting those different values, and then the height of the bar is the count. There is one weird thing with this plot, is that it's giving you the axes from like 0.5 to 0.5 and then 0.5 to 1.5, etc. And that's because when I talked about data types, R is treating the recurrence column as a number and not actually as a category. So it's seeing 0 as in the number 0 and 1 as in the number 1, and not 0 as in like category, like discrete category value 0 and discrete category value 1. And you'll see this a lot depending on where you get your data sets from. A lot of data sets that come with, so for example, I think like a lot of these longitudinal health data sets like NHANES or whatever, they have a data set and then they have like this many page code book that it comes with it. And that's because when you go and download the data set, all you see are numbers. And then you have to use the code book to assign like, oh, 0 means this and 1 means this and 99 means missing and et cetera, et cetera. And if you try to load that into R is just going to see that as a number and not as actual categories. So how do we fix this? Or another way to say it is, how do we change from one type of variable to another type of variable? So let me copy and paste that block of code again. I am going to put a new line here just so it's a little bit less wide. So this is the same exact plot. So as long as you're within like a set of round brackets, you can put in extra line breaks and nothing bad will happen. So recurrence right now is treated as a number or as a numeric value. We want it to treat it as a categorical value. The R way, or a lot of programming or some programming languages called categorical variables, they're called factors. So in R, if you want to turn something into a factor or into a category, we say as.factor. So this will say, whatever column this is, turn it into a factor. Another way of saying that is turn it into a category or categorical value, and then do the plot. So now the figure actually looks a little bit better because it's 0 the category and not 0 the number. All right. So before I go on and show you the next group, a lot of times you'll see this code written in slightly different orders and essentially missing certain words. Usually no one says mapping equals. It's usually you'll see the code written as, we know the first thing is going to be the data set, the second thing is going to be the mapping, and then we're going to add in the layer. So that is essentially the equivalent to the code that we've been working with. Another thing because it's a layering system, we can add or associate different layers to different parts of our plot. So sometimes you'll see this same exact code written as, here's just the plot data set in the ggplot layer, and then I'm going to put my mapping layer in the actual geometry layer. So I'm saying like, hey, use the figure here, but then for this bar plot, use this as the x-axis and this as the y-axis. Why is this useful? Because it's not very useful now, but you can literally overlay two different types of plots, one on top of one another. And that's sort of the flexibility that you can do by just moving different components of the layering system around. So that's single categorical values, and using plots is a really useful, using bar plots is one useful way for that. What happens if we have an actual continuous variable? Usually you do that with a histogram. So we can draw a histogram using ggplot. We're going to put in blood storage. I'm going to put in AES. X is going to be, sorry, lowercase x is going to be the age group. So let's just figure out how old are these people. I'm going to assume they're going to be, you know, over the age of 50 because of the type of treatment that they've undergone. So we have pretty much the same bit of information as before, but because now it is a continuous variable, it doesn't make sense to use a bar plot to count things. We want a histogram to get ranges of things or counts between ranges. And so we can create a histogram by saying geom_histogram. When you run this, by default, it will only max out at 30 bins. So if you have too much of a wide of a range, it's just going to pick like 30. So in here, it says using bins equal 30, pick a better value with bin width. So what we can here literally say bins is equal to 10. And then we get a histogram of 10 values, right? And so this is useful because sometimes you need smaller bins to really get a sense of like where the what the actual distribution is, right? So if it's too fine, you're not gonna get the actual overall shape. If it's not fine, like if I just say like bin is 2 or bin is 1, it's really not gonna be like very useful unless you're trying to recategorize people just so you have like equal number of groups into things, but that's also going to have other statistical ramifications that you have to think about. So it's not always as simple like, oh, I'm just going to calculate the mean or median, use that as a cutoff, and then just create a new category between those two. That's not always a good thing to do. And it's also in my head as one of those, like if I ever end up doing that, I have to go look up more details as to what I'm doing, because it's just one of those things that's like, that's something I definitely need to look into. So, all right, so what about figures that are using multiple variables? So this all points back down to everything we talked about until now about tidy data and pointing to specific columns. So there is a column called tval. So if I say names of blood storage, there is a tval column, and it is a column that represents the tumor volume as a ordinal variable. So it's either 1 for low, 2 for medium, or 3 for extensive, right? So it's a categorical value. So what if my question is, if I have a category of like these different tumor volumes, like does age play a factor into this, right? Like, could it be that if you're older, maybe you're getting a bigger tumor? I don't know. Let's just do that as a quick data exploration exercise. So I'm going to say ggplot blood storage. I can put the AES here. That part doesn't matter right now, but I'm going to add in geom_box plot. So in this box plot, I'm going to put in my aesthetic mapping, so AES. So this is the mapping equals aesthetics. And in here, I say, what do I want on my x-axis? What do I want plotted on my y-axis? So I can say X is going to be my tumor volume column, and my Y is going to be my age column. So it's going to try to do this. But again, this is the same problem we had before. Tumor volume, because it's values 1, 2, or 3, it's treating it as a numeric column, not as an actual categories. So we have to do the same little tweak in our data, or tweak in our plotting code, just like before. And we can say as dot factor, tumor volume, and then Y is the age. And now it understands like, oh, okay, I understand how to draw box plots when of different groups. I'm going to treat tumor volume as a category. Here's the box plot across each group. And it's also nice enough to tell you like if it's missing, that's the missing thing, missing column. Don't ask me too much about what that is. I have to definitely do more exploration to this data, but for teaching purposes, that's usually good enough. One type of plot that I like to use, whenever I plot a box plot, I always make another type of plot called a violin plot. And I will show you why. So if I run a violin plot, this is the violin plot. So if you've ever seen, like we just saw before, the histogram of age, a violin plot is if you took that histogram, rotated it 90 degrees, and then mirrored it, that is the violin plot. Why does it look like, why is it called violin? Because sometimes if you get weird distributions in your data, it will literally look like a violin. And I like looking at violin plots because it can overemphasize whether or not there's like weird skews in your data because it's actually just plotting the histogram. And so if I compare between the two, like which one of these data sets is normal or more normal than the other, sort of, I always just look at the two together just to help me like get a better sense of where things are. Another thing that's also really useful, and this plays a role into the layering system, is I can add in literally another type of plot on top, right? So I can say plus geom_point AES, and literally the same X and Y factor. So I can literally put in a scatter plot right on top. And so now on top of either the box plot or a violin plot, I can get a set of like, here's actually where all the points are. Or instead of geom_point, there is another type of point called jitter. And instead of just having the points like as they are in your raw data, it sort of just jitters or moves them around a little bit, just so you can have a better sense of where all the points are. So you can either do this on top of the box plot or on top of the violin plot. So if you're not used to looking at box plots, you can just throw on top the actual scatter plot to give you a sense of like where all your points are in your data set. And the other thing here, having the points is nice because you'll know that like the NA actually just has very few people in it. And that's something that doesn't just show up just looking at box plots. Like you have no sense of like, oh, is this like an outlier because like there's thousands of people and this is like an extreme outlier? Or is it like it's an outlier because the way box plots are calculated, but there's only like 5 people? So yeah, you can also do the same things by saying like group by this and then running the count or like the n function that I showed you. But you can also very quickly get the same answer or the sense of what's going on with plots. Another way to rewrite this, and this is sort of like what's nice about the layering system, is if you put something at a lower base layer, it carries over to the upper layers. So if I just say like, hey, I want to plot X and Y, even though I haven't told it what plots to make yet, I can tell it like, hey, plot the box plot using that data set, plot the jitter plot on top of that using the same data set. It's literally just pulling, if it needs something, it just pulls from the underlying layer. So you can mix and match different data inputs if you need to. That is the flexibility that ggplot gives you. So let's talk about more variables getting input into a plot. All right, so if we look at the names of our data set, blood storage, there is a variable called tumor or p volume, which is the prostate volume in grams. So that is a continuous variable. There is the pre-op PSA. So this is the some antigen level measured in nanograms per milliliter. So that's also a continuous variable. So if we have two continuous variables, we usually plot a scatter plot on them. And so let's plot a scatter plot using this data set. So we can say ggplot, data is blood storage. I can say AES X is equal to the volume, Y is equal to the pre-op PSA, and I'm going to add in geom_point for scatter plot. So how do we add in more data to this figure? So let's say there's another variable in here called the surgical Gleason score. And so that is a categorical variable that goes from 1 as a not in sign, 2 for no residual disease, 3 for a score of 7 or above. So 3 for a score of 7 and 4 for a score of 8 to 10. So that is a categorical variable with values of 1, 2, 3, and 4. So it would be nice to see, like, how does this figure change depending on some other thing of the categories? So what we can do here in this aesthetics, so remember in the AES, this is where we say like, hey, I want something to be values of that column. We can say color is equal to SGS. And now we will get the same scatter plot, but it's colored by different values of that categorical variable. So I'm going to clean up that part a little bit, but this SGS is the same problem we had before. It's showing up as 1, 2, 3, 4. R read it in as a number, so we want it to be read in as a category. So we say as dot factor of SGS, and then we actually get instead of like a continuous range of colors because they're actually different, we get an actual different color point, so we don't have to worry about colors getting blended together and stuff. There is a little issue with this figure, so there's a bit of overplotting, so a lot of points are clustered in the same location, so that becomes a little bit hard to read. So there's other ways we can modify that. So we can say here in geom_point, instead of just AES, we can say outside of AES. Now we're just talking about the actual point itself. We can say, make the actual point like a little bit transparent, right? So that is one way that can kind of help you with overplotting, is if we just make the points a little bit more transparent, you can see behind them a little bit easier. And that's using alpha is 0.05. So that is different from saying alpha under AES, because then that assumes there's a column called alpha and you're using that as some plotting categorical variable or something. This part of alpha that's outside of the AES block is referring to the actual geometry or the actual point itself. So I'm going to copy that little block of code again, remove the alpha. At the very beginning of this part, I talked about facets and how it's just easier to show you than to try to explain. So essentially a facet is, I'm given this plot, but I'm going to draw the same version of this plot with a different subset of the data. So it's very similar to, like, you know, how group by was able to break up my data into all of those variables, do a thing, so split, apply, and then combine. Facets is the group by version for plotting. So it can split my data based off of a variable, apply a function, which in this case is apply a figure, and then put it all together for us all in one go. So that is a facet. So how does a facet work? Well, from ggplot world, facets are a totally separate layer. So we add in facet. And if we sort of type in FACE, we either get facet grid or facet wrap. The way I describe, the way you can remember this is a grid is usually like a two-dimensional grid. So there's two variables you can specify, and a wrap is just one, and it'll just keep going as if you're reading text. So depending on if you're trying to plot more than one categorical variable or one or two, you'll use grid or wrap, and I'll show you both. Let's first start off with wrap. The notation is going to be a little bit weird, but we put the little tilde symbol. So this is shift key to the letter key to the left of the number 1, or shift 6 if you're on another keyboard layout, or 8. And then in here, just like AES, we specify the column we want to use. So there's another column called red blood cell age group. So we can say r.rbc.age.group. And what this will do is the age groups come in 3 different age categories, 1, 2, or 3. And what it's doing is it's taking that scatter plot that we already specified and redrawing the scatter plot for each one of those groups. So it's a way to, 1, help you with overplotting, and 2, if you have other variables or other categorical variables of interest, it's helping you figure out like which one of these is actually like more related to some other variable. And just to round off the example, I'm going to copy that block of code and I'll put it in there just so people have it. How do we use facet grid if we want to specify 2 variables? So there's another one called facet grid, and we use the same tilde notation. So there's rbc.age.group tilde, and then to the right or left of the tilde, we put in the other variable. So recurrence, because that is our variable of interest. Maybe these are all of the variables that we're going to put into our model. So we have recurrence of 0 or 1, the RBC age groups as 1, 2, and 3, and then we have the volume by pre-op PSA of the scatter plots, and each color is based off of the surgical Gleason score, et cetera, et cetera. If you want, you can add in size or shape equals under AES if you're trying to put in more variables. Just be careful with size because circles don't scale linearly. Like a circle twice as big doesn't mean a radius twice as big. That's a circle 4 times as big. So be careful with size, but you can still use size. And with shape, you want to be careful with shapes as well, because sometimes they may be hard to distinguish. So it's also okay to use multiple visualization inputs. Sorry, whoops. So instead of just, let me finish the thought. It's okay to use multiple visualization inputs for the same variable. So instead of just color for surgical Gleason score, I can also put shape. And then this way you have 2 variables sort of representing the same thing. And maybe that'll help, split out things for you. So there are a whole bunch of other techniques that you can do on that end. And then last but not least, I will just keep working on this thing. There are themes. So remember the last part. So we can say theme underscore. There are built-in themes. So if you really don't like the gray background, which I really don't, I like using theme minimal, and that will throw away a lot of the excess. There's also a whole bunch of other themes that you can use as well. I don't know if I have it installed on this computer. There is a library called GG Themes. Sort of the fun thing about that is you can have your plots look like other things. So before going into that, another thing with ggplot that you can do is you can save them into a variable. So this is my plot. It's just that, and I can just re-show the plot just by using G because I assigned it to G, or you can call this, I wouldn't call this plot because plot actually is a built-in function. So you can call this G for your ggplot or whatever. And what's nice about that is because that's saved as a thing, you can literally add in other layers. So let's say I want to say theme underscore, because I loaded up GG themes, like here is like the Wall Street Journal theme for this plot or whatever. So that is just to say, if you are working in a lab, or if you can write a lot of your R papers, journal papers in R, and a lot of times you might find someone has put together a theme or a set of colors and stuff that match a particular journal. And so you can literally say like, here's my figure. I don't want to spend too much time like tinkering with font sizes and whatnot. So there might literally just be like plus theme underscore like journal, and it might do it for you. Or at least it will get enough of the theme components fixed for you, so you can like go and tweak them further if you need to. All right, we'll take another 5-minute break. In the meantime, this is the exercise that you can work on during the 5 minutes. So we'll come back at 7 past the hour, and then we'll finish up on statistics with logistic regression, and then we will sort of just conclude this little smaller block of the workshop. All right, let's go through this problem. So the first problem, the different parts was load the cytomegalovirus data set. I can never pronounce that word, into a variable called CMV. So this is really just saying, and we should have or could have done this with our blood storage data set, was rename it blood instead of having to type blood storage over and over and over again. So I'm going to rename the CMV data set that comes out of medical data as CMV, just so it's less typing. The next part was create a bar chart of the CMV response variable. Yes. Okay, so we have ggplot, and the data set that we're passing in is CMV, and we're trying to create a bar chart plus geom underscore bar, and it's going to be AES, X is equal to CMV. And so we see here, this is a data set where, and I should have explained this, the contents of this data set. I realized this is the topic of the next section, but this is a data set on whether or not, I believe this is if you are cancer positive or negative, or at least CMV positive or negative. I have to check on the next page of notes. But you see, this is the same problem that we had before, where there was 0 and 1 as a binary variable, but it's being read in as a number. So if you want, you could have turned that into a factor by putting as.factor in there as well. I didn't put that as part of the scaffolding code, but that is something that you could have done. But if it's just for quick visualizations, you don't have to. The next part was a bar plot of prior dot transplant covered by CMV values. And so that is ggplot CMV AES give me 1 second. X is as.factor CMV. Sorry, it's a bar plot of prior transplant. So it is prior dot transplant plus geom underscore bar. And then we can either put in the AES fill here, or we could have put it in above. That part doesn't matter. So we can say fill is equal to as.factor CMV. I hope I did it right. And then this is how you can get a sense of their prior transplant status, 0 or 1, like no, they didn't have prior transplant status, 1, they did have a prior transplant. And then for bar graphs, if you use the fill parameter, you can actually have stacked bar graphs. So this is the total count, and then it's filtered by those two components. If you want, there is another parameter in geom bar. There is something called, I think it's position equals dodge. So instead of having stacked bar plots, if this actually plots, is this too big? Yeah, so instead of having them stacked, you can have them like dodged, which is the ggplot way of saying plot those two things next to each other instead of stacking them on top. And so you can get like a more accurate count between that. And then the last thing was take this plot and facet by both donor CMV and recipient CMV. And so that is the same exact plot here. And then we're saying use facet underscore grid, because I'm saying using these two variables. So it's going to be donor.cmv tilde recipient.cmv. And then I hope I am doing this correctly. Yes. And then so you can have the different components all filtered out and stuff. And one thing you'll notice here is that for the donor 0, recipient 0, like there are all have no prior transplant, and that makes sense because they weren't a donor or a receiver. So you'll see like big holes in your data because like one, it doesn't apply. It's like very similar to seeing like, do you have pregnant males in your data set? Probably will have like a bar or a blank line somewhere there. Okay, so last topic is on fitting models. And I guess I picked logistic regression as the topic to introduce just statistics in general, because that's sort of the most important thing that we learned in my master's in public health program when I was doing epidemiology. So, and at least for most medical researchers, like the easiest form of the question you can ask is like, did something happen, yes or no? So that binary response is really common in medical research. And so I sort of just picked, if you're working with a binary variable, let's just show you the statistical method for working with binary outcomes. And that tool is called logistic regression. So we talked a little bit about nominal, ordinal, and binary variables. So logistic regression happens when your outcome of interest is binary. It doesn't mean that the inputs or the x's or variables, they can be whatever you want them to be, but the variable of interest, so your y, your response variable, your dependent variable, that is binary. And so just as a really, really short recap in how to draw a line through your data, if you heard of the phrase like y equals mx plus b, that is the formula for a line through a, it's not really through a set of points, but it's the formula for a line. So the m is known as the slope, the x is the value on the x-axis, the y is the value on the y-axis. So when those two come together, there is a point there. The m tells you how steep that slope is, and then the b is essentially saying where that line starts. So if b is 0, it's going straight through the origin or the 0, 0 point. But most of the time, our data doesn't just go through 0, 0, it's starting somewhere else. So that's just fitting, drawing a straight line on a piece of graph paper, right? So how does this come into play when we're trying to work with multiple variables? So instead of saying mx, what you'll see is beta x. And so when you talk to public health people or biostatisticians, they will talk about the m and they will use the term beta. And so they will probably, you'll probably hear people say like, what are your betas? What is beta 1? And so your betas is another term that you will see for your input variables or your variables of interest. So when they ask about what are your betas, they mean like, what is the value for age, or how does age relate to your variable of interest? So if we have multiple variables, like multiple columns like that we can point to, each one of those columns become a separate beta. And so if I were to say like, oh, this person was 56 years old with a volume of this, with a pre-op PSA of this, with these two other volume values, plug all of that in, and whatever comes out as my y, that will end up being the value of the y. And so that's why you also see people call these x's and y's, and that's part of the mathematical notation for all of this. So that's drawing a straight line. So what I showed you about like y equals mx plus b, that is like the thing on the left, which is linear regression, drawing a straight line. That's great if you are trying to predict something like what is the age of someone. It's probably going to be more than just values of 0 and 1. So if we have a data set and its only potential values are 0 and 1, it's probably a very bad idea to draw a straight line through all of them. Like, does the line on the left fit your data if it's only 0 and 1. It literally goes off into infinity on both ends, so it doesn't make sense to draw a straight line through them. And so logistic regression is literally some transformation to the straight line that bounds everything between 0 and 1. And so that is when people are saying like, okay, this is the right model for your data. It's because like, yeah, it's bound between 0 and 1. And so like if your data is only 0 and 1, that's probably a better model than if your data is 0 and 1, and then it's bound between negative infinity and positive infinity. And so logistic regression is literally linear regression plus some transformation, and then you get logistic regression. So all of the parts about logistic regression, so if you just look at this middle part here, is exactly the same. We've seen that. What makes logistic regression is that transformation function, and this is probably all the math that you'll ever see, is this function called logit, and it's literally calculated. This is the actual formula for it. The reason why this is important is because when you fit a logistic regression model, because it went through the logit function to give you the model, you essentially have to undo the logit function to the results to actually interpret the results. So if you look here, we have the log of this p over 1 minus p is called the odds of something. So think of odds as like the probability of something happening. It's just technically that's not true. There's a slight difference between probability of something happening versus the odds of something happening. But just as make things a little bit simpler and just to get the general gist of it, you can sort of treat them the same, but they're technically not the same. And so if we look at these two lines here, it's essentially drawing a straight line, but there's this weird logistic transformation or logit transformation. And we have to undo that part of it. The way we do that is to undo the opposite of a log transformation is to exponentiate it. So if we want to get rid of that log, we exponentiate everything. And that's why when you look at logistic regression output, everyone talks about their values as odds ratios. And it's because you have an odds. And so that's essentially how logistic regression works. And so in a nutshell, it is literally just drawing a straight line, except there's this transformation function that you have to undo or partially undo to make sense of the output. Because otherwise, you're going to get a number and it's going to be like, this is the log odds of this happening. And it's like, what? There's no conception of log odds versus like, this is the odds of something happening. Actually sounds more like English. And because it sounds more like English, you can probably get a better sense of what's going on. And so that's why you hear about the terms beta, and that's why in logistic regression, everything's talked about in odds ratios or odds, and this is the reason why. The way we do this, because R is a programming language essentially written by statisticians for statisticians, a lot of the statistical models are all built in. So we don't have to load up a brand new library for it. I think next week I might show you something called tidy models, which is more of a machine learning framework. But if you're just trying to do statistics, and also this is a much easier way to introduce you to all of these concepts, it's all built into R already, and you don't have to do anything special. So let us create a new script. I'm going to save this. This is going to be 07 logistic for logistic regression. And I am going to go to session, restart R. I'm going to load up the medical data library. I'm also going to load up the, tidyverse library, just so we have everything, just so I'm not typing blood_storage over and over and over again. We can save this as blood gets blood_storage, just so we don't have to, just so there's the less typing. All right, so the blood data set we worked on for the visualization, what was the variable of interest? That variable of interest was the recurrence variable. So how do we go about and fit our logistic regression model? So logistic regression is a linear model. So we use this function called generalized linear model or GLM. And in here, fitting a model is actually, in terms of the amount of code needed to fit a model, it's very simple. So in here, we specify how do we, what are the variables we want involved in this model, right? So just like how it's y equals mx plus b, it's going to be y is the variable of interest. So for us, it is recurrence. Instead of equals, we literally put in tilde, and then everything else, the beta x plus beta 1x plus beta 2x, et cetera, we just add in those variables. So let's say I want to see how does age relate to the recurrence variable in our data set. And that's how we specify all the variables involved to fit a model, right? So that's why tidy data stuff becomes really important, because if you want that column or a specific variable to be an input to your data, you have to make it an explicit column. And then go back to the tidy data stuff to figure out how to make that a specific column. So this is known as a formula in R. So this is the formula notation for specifying a model. We told it the columns involved in our model. Then we have to tell it what is the data that we want. Because we're using a function called generalized linear models, we also have to tell it which form of linear model we want to calculate. And so we say family is equal to binomial. And that's how we fit a logistic regression model. That is essentially it for almost all of the stuff around machine learning. The actual part where you get to fit the model is like 1 or 2 lines almost all of the time. Everything else is trying to figure out how to get values out, interpret values. So if I run this, you'll notice some of the output came out. Let me just save this to a variable called mod1. So we have model1. I can look at model1 just as the results, and you'll see it gives me the intercept and the age. So this is the m in mx plus b, and this is the b in mx plus b. And if I plug in any, like let's say I'm 55, it's going to be 55 times that number minus 2.51, and then that is going to be the value for recurrence. And again, that is the log odd, so we have to do a whole bunch of other weird things with it. Another way, and if you are coming from statistics world, just looking at this is useful, but what you want to do, there's a built-in function called summary. And if you give the model, if you pass in the model into summary, you get a lot more of the actual parts to help you figure out whether or not this is a good model or not. I guess most interest is this section called coefficients. And yes, you get the p-values for things, you can figure out if it's less than 0.05, et cetera, but the coefficients part is when people talk about betas or beta tables, this is the part that they are referring to. At the bottom, you have something called the AIC. Essentially, this is only a number that's useful when you're comparing multiple models. So just this number on its own is not useful, but this is one way where you can figure out, is one model, quote unquote, better than the other model? And there's many, many different ways where you can answer and define better. But this is why using summary is helpful, because it gives you a little bit of everything that's going on. Another thing that's really useful, because we talked about running data frame objects, because you want to either plot the results or you want to do some transformation, because like, what is this value? How do we interpret this number? And we want to be able to transform this into a number that's like more interpretable. And so in regular linear regression, if we weren't doing logistic regression, we would get the same table output. The way we would interpret this, if this was regular linear regression, would be for 1 unit increase in age, our outcome variable will increase by 0.01 points or whatever the unit is. Because this is logistic regression, the way we interpret this number is for every 1 unit increase in age. So like if you're going from age 55 to 56, or if your values, whatever. So for every 1 unit increase in age, the log odds increases by 0.01 times, right? Because there's that logit function. And so what is log odds? That kind of doesn't really make much sense. So we want to be able to pull this information out as a regular data frame so we can do other things, mainly so we can get a value that's a little bit more interpretable. So the R ecosystem has a tool for doing this easier. There is a library called Broom, and you'll also know, eventually you'll realize that a lot of the R libraries have puns. And so Broom is the library that literally cleans up your model outputs. So sweeps up or brooms your model outputs. In Broom, and I kind of wish they didn't call it this function, but they sort of have a claim for this now because they made it first. In Broom, there's a function called tidy. And if we give tidy the actual model, so like the entire fitted model, not the summary, not the output of summary, but the original fitted model, its output will just give you a nice data frame of your coefficients. So if you fit a model in R and you're just like, whatever, I just need this set of values written out to a CSV file or to an Excel file, there you go. You have a data frame object. Refer back to yesterday using write CSV or write Excel to save out this information as a table that you can do for other things. One thing we're going to do with this, so I can save this as a value called results. So I'll call this res1 for results1. And that's our value. I'm going to show you another useful tidyverse function. So we showed you yesterday, like select and filter and et cetera, et cetera. I haven't showed you how to create new columns or make new calculations off of columns. That function is called mutate. So mutate mutates an existing column or creates a new column. So it mutates the data frame. So if we want to create a new column, just pretend it always existed, and we can say odds. Odds is going to be equal to we will exponentiate the values of estimate. And then all it did was exponentiate the estimate column, and that is the odds. So now our interpretation is for 1 unit increase in age, the odds of cancer reoccurrence increases by 1.02 times. So that is really the only technical acceptable way you can interpret that number. And that sentence makes way more sense than the log odds of 0.015, right? So the way this number is interpreted in every beta coefficient or odds ratios that you do in logistic regression is for every 1 unit increase in age, the odds of cancer reoccurrence going from 0 to 1 will increase by 1.02 times. And that's really it. That's the entire process of fitting a model. And so we can literally go through that and add more variables to the model, because like I said yesterday about Simpson's paradox, just because you have some pattern going in one direction, that doesn't necessarily mean it's the same pattern in subgroups. And for most of the time, you're more interested in how different subgroups behave than the overall population. And Simpson's paradox is what happens when the subgroup analysis is literally in the opposite direction than the overall finding. So let's create another model. So I'm going to call this mod 2. We're going to use GLM. And how do we, so our original variable was just recurrence and age. So how do we add in more columns to our data set? We literally put in a plus sign and then put in other variables. All right, so if we want the volume and pre-op PSA status, we literally add them to the formula statement. And that is it. That is how you build up different models. The rest of the code for the model fit will be the same. So we're still using our blood data set. And in our case, we are still using logistic regression. And then the results are almost exactly the same. So I can sort of skip the step and then say tidy of mod2, and here are my betas. And you can see here, I get the little table of my results. And so now if this is the new model that I want, I can save that. You'll notice that I have the AIC for this model. And if I were to compare 265 with the original one, which was 292, and I believe AIC is lower is better. The second model is a little bit better than the first one. And that's just one piece of evidence as you're comparing models. You still have to make sure that your model makes sense. And then if we want to interpret this model as a human, we can then pass this data set after it gets passed in through tidy. So let me, mod2 goes into tidy and then goes into mutate, and odds is exp of the estimate column. And now we can see something else. So the odds ratios, typically, if it's near or if the odds is 1, essentially it means there's like nothing going on, right? And if I say the sentence again, for 1 unit increase in age, the odds of having cancer reoccurrence increases by 1.03 times. That's because that's very close to 1. It essentially, like, what is some number times 1? It is that number. So the odds increasing is very small. But if it's below 0, so this is interpreted as for 1 unit increase in the volume of the tumor, the odds of being the odds of having reoccurrence increases by 0.92 times. So it sort of seems like this is more or less protective, I guess. But that's how you interpret those values. The other thing you want to keep in mind when you're interpreting odds ratios is what is the range of numbers? So the range between 0 and 1 in terms of odds ratios is the same amount of quote unquote distance from 1 to infinity. So you'll never have an odds ratio under 0, but 1 is sort of like that cutoff of like quote unquote nothing's happening. And so the way you would start using this model is, let's say you have a brand new patient that comes in, you collect their age, you get their volume, you get their pre-op PSA status, and then you literally plug it in and you take the number that you collected, multiply it by that, add all of those pieces together, and then you get your log odds for whether or not they're going to be, whether or not they will have a recurrence, yes or no. The last model I want to show you is what happens when one of those variables is a categorical variable. I'm going to do a little bit of copy and pasting because a lot of it is the same. So in this case, remember the tval variable. That was a categorical variable that represents the tumor volume. So that pval was something different from tval. I mixed those two up. But the tval volume either goes into 1 as low, 2 as medium, or 3 as extensive. So this is technically a categorical variable, not necessarily a numeric variable, even though it's ordered. So if you do end up with categorical variables, you can put that into your model. You do have to do one more extra step. Yeah, okay. So the value will, like the model will still fit, and you'll see that like when we put that in, like, yes, tumor volume does seem to be a very significant variable, and it does make sense. If your tumor is bigger, then it's probably more likely you're going to have a reoccurrence after surgery. So the way if we use the same sentence, it's for every 1 unit increase in this category. Maybe in this case, because it's ordinal, it makes sense. But if this was, for example, like gender status, what does it mean for like 1 unit increase in gender status? Like that does not make any sense, right? So we have to do something a little bit different when we are working with categorical variables. One, if your data is encoded as a number, you definitely have to make sure it's a factor. So the easy way to do that is just like in plotting, we wrap it around as.factor. And then if we look at our results, the output is a little bit different. So before, where it just said tval, it is now tval2 or tval3. This is known as, in statistics world, dummy variable encoding. In computer science / engineering world, you will hear this as one-hot encoding. And essentially, it is if you have a bunch of categories, your data essentially needs to be a number. So even though it's like, if I say sex is MALE or FEMALE, and the computer will still need to encode it as 0 and 1. But what a dummy variable is you will create a separate column for each one of those categorical values. So when I dummy encode my data set, because tval has 3 different values, under the hood, it will create 3 different columns: tval equals 1, tval equals 2, tval equals 3. And then it will populate that number, that column. It will give it a 1 if that's the value it got. It will give it a 0 if that's not the value it has. So I guess because, so let's go outside of this context. Let's pretend we have a data set and one of my variables is smoking status. I can either have a smoking status of 1 for yes or 0 for no. So it'll be YES or smoker or non-smoker. If I dummy encode it, I will have 2 variables, one called smoker and another one called non-smoker. And then for my value, for like Daniel's value, it will have 0 for smoker and 1 for non-smoker. And that's dummy encoding. The reason why you don't see tval1 here is because when you're fitting linear models, if you have 3 potential categories, if you know the status of 2 of them, then you automatically know the status of the last one, right? So if I know the status of whether or not I'm a non-smoker, then you can infer whether or not I'm a smoker. So here, if I know the status of tval2 and tval3, then I definitely know the status of tval1. So if tval2 and 3 are both 0, then I definitely know that it's this particular person has the tumor volume classification of 1. When you look at your statistics output, I went through all of that information about dummy encoding in a lot of detail, is because the one category that is missing is the reference value. So when I say 1 unit increase, it is now going from the one that's missing to that value. So this is going to say, the way I interpret this is going to be for a person that has a tumor value, a tval value of 2, the log odds of getting cancer reoccurrence increases by 2.073, the log odds of 2.703 compared to a person with t-val, compared to a person with t-val of 1. So that dummy variable encoding, that reference value is really important because that tells you how you can interpret that number. And so just going on, so I can have like a more sensible sentence being formed, I can pass this to tidy and then do the same thing where I'm mutating odds is equal to exp of estimate. So the way I would interpret this, so let's use this extreme case. For people who have a tumor volume of 3 compared to people who have a tumor volume of 1, the odds of having reoccurrence increases by 22.6 times is how you would interpret that sentence. And that is different from how I would interpret a regular continuous variable. And that's because of the dummy variable encoding. And the nice thing about R is all it takes is saying as dot factor, and it will automatically dummy encode it for you. If you've worked in SAS and other languages, you sort of have to process part of that on your own. Just as a quick thing, so now that I have this data set, let's save this to a variable, mod 3. I can call this OR. And because it's a data frame, let's go and review some of the stuff with our plotting that we just did. So let's say I have ggplot. The data is going to be mod 3 OR, and I want to plot my coefficients. So I have AES. What's going to be my x-axis? So I want my x-axis to be the term. So x is equal to term. Y is equal to whatever the value for odds is going to be. Because it's two essentially numbers, I'm going to say geom underscore point. And I can plot my coefficients. One thing that is sort of annoying when you're plotting coefficients is if things overlap. Yes, you can sort of tilt the axis labels, but a nice quick trick is to literally pass in the layer called chord flip. And all it does is flip your X and Y axes. And so you don't have to deal with the weird like text overlapping one another. And so these are your coefficients. It goes from 0 to 1 and then 1 to infinity. And one other thing that you can do is you can put in a line. Y-intercept is equal to 1. You can literally draw in a reference line, and essentially anything that is far away from that line is probably an important variable. So you can see like the tumor volume are definitely very, very involved with whether or not you're of your recurrent status. And then if you were to do this for a real paper and you're trying to present these, you would actually calculate confidence intervals on top of the odds ratios and then draw the bands around them and stuff like that. But that's how you can use plotting with your model fitting, and all of that again ties back into how your data is formatted, because you still have to be able to point to columns for all of this to work. Right. So again, it wouldn't make sense to point to the column that says like male 014. I would want a separate column for like sex and age group. All of those tidy data issues, like when you see them, try to fix them, because you probably will end up needing those as separate columns like right away. Okay. So that's it. That's really everything. I'll go through a few concluding slides that have a bunch of other resources available. So hopefully this was a small, gentle introduction to programming in R. Hopefully you find something useful to the work that you're thinking about doing. For additional resources, and you can always find this on the bit.ly link. And after today, when I get all of the videos uploaded on YouTube, I will post all of this stuff in a follow-up email. So there's a whole bunch of free resources. There's the R for Data Science book that is more general purpose. If you need help, the R for Data Science community literally has a Slack group. In that Slack group, there are literally people who have open office hours. So if you have R problems and there's no one sort of near you to ask questions for, sign up to go to one of their office hours. It's a free service. Go use it. If you want to practice, there's a thing on Twitter called Tidy Tuesday, where every Tuesday a brand new data set gets released, and you can see everyone on Twitter sort of make plots out of them. And usually code gets shared with it. So if you want to see a lot of this other stuff in practice, you can. If you just want to listen to people or just see things work in real time, David Robinson and Jesse Mostapak both have either a YouTube live stream or a Twitch live stream where they literally are like, oh, it's Tidy Tuesday, let's just go through a data set. And they spend an hour sort of just going through an analysis and talking through it. So if you want to see a lot of this stuff that we covered today, like in practice, you can. If you identify as a lady, there is a Slack group for the Our Ladies group. So another resource to ask questions that you can join. If you are in the medical community, there's also a conference Slack help group specifically for our medicine folks. And if you just want more R resources just to help you consolidate information, there's literally a resource called Big Book of R, which the material for this is also listed under. So if you are looking for something like genomic specific, like take a look there to see if there's already like a genomic specific set of curriculum, books, data sets that are all free and public that you can go to. If you're at Virginia Tech, in the Blacksburg campus, there is the data services group that you can use. That's sort of where I am and my advisor, Anne, is at. And if you are here in Roanoke, the Center for Biostatistics and Health Data Science, which is literally around the corner from this room, in that suite over there, Alex Hanlon runs that group. There are 2 open office hours on Monday and Wednesday. If you literally just have a stats question, just call into their Zoom thing and there's going to be a person to help you with whatever stats problem you have. So that is a resource that you have here at Virginia Tech. For other things, if you're just looking for other materials to read through, the Carpentries is one of them. And depending on what you need, there probably is already a curriculum for it. So if you're also involved in social sciences or geospatial, or you're trying to work with maps and stuff, they have separate curriculums around that that use R or Python. And you can look into that information as well. Last but not least, so there is a post-workshop survey. It's in the email/calendar invite. So if you can, please take the post-workshop survey. It'll help me graduate, and that'll be great. And that's it. Yeah. So if you have any questions to you or anyone else, you can ask them away. And yeah, so we'll just hang around until everyone sort of just leaves.